This is Unit 2, Video 3. In this video we will talk about something called ionization energy. And you hear the word ion in here, which will mean that the atom either loses or gains an electron. So the ionization energy is actually specific to losing an electron. So here we say that ionization energy is the energy required to remove an electron from an atom. And because we're talking about energy, the units will be kilojoules per mole. Usually everything is expressed in per mole when talking about elements. So here you have an atom, and when we remove the electron from the atom, you become an ion. Now remember, you become a cation, a positive ion, because anytime electrons are removed, the positive charge results. IE1 would be the designation. This is ionization energy of the first electron. It means just you're removing for the first electron. IE2 removing the second, and on, and you can talk about IE5, IE6. And here it says ionization energies are endothermic, which means energy is absorbed. The reason it's absorbed because you are breaking a bond, in essence. You're technically breaking the bond between the electron and the nucleus. So because you're breaking that bond, you have to put energy into breaking any sort of bond in chemistry, and that's why they are endothermic. Now the trend on the periodic table is given right here, and you see a nice, neat trend. In general, you see, so here we have ionization energies across the y-axis. We go all the way up to 2500, and most ionization energies are within 1000 or so. And as you'll see, some of them, especially the noble gases, have the highest ionization energy of all. But and we're ignoring the d block elements. The d block elements, you'll see, are pretty stable in terms of they're about the same ionization energy going across, so we don't see a very big trend there, but we definitely see a big trend in the main group elements, and this will tell a very important story. So here it says ionization energy decreases going down a group. Now down a group means down vertically down the periodic table, and the question is why. And well, we also increase across the period. Here it is. So we're going to answer the why question about down a group first. So here it says down a group, electrons from the previous shell shield the added electrons from the nucleus. So anytime you're making a new shell, so say this is shell 1, if you make the second shell, shell 2, the electrons in shell 2 are now shielded from the nucleus, which is positive, which wants to attract and pull the electrons in. They are shielded by the first shell. Now that does not happen if you go across a period. Across a period, you're being added to the same shell, and so there's no extra shielding, which means the nucleus just keeps pulling the electrons closer and closer. And the shielding is actually the important word. And this shielding explains essentially why the ionization energy increases, because the pull becomes stronger, there is no shielding. And here it explains why ionization energy decreases, because there is shielding from the nucleus, and the electron's pull is not as strong, is the idea. So the key word here is shielding, being shielding. So you want to be able to use that word as you're describing this trend of ionization energy. And this actually explains the reactivity. We'll talk about reactivity of, say, group 1. This is group 1, the alkali metals. And you'll see that the reactivity increases as you go down. So for example, potassium is much more reactive than sodium. Now a fun way to react these, and hopefully you'll see this in class, is by simply throwing these elements into water. So here you have sodium being placed into water, and notice it ignites. You see there's a little bit of a flame that develops. If you throw potassium into water, the same thing happens. It also ignites, but there is a much more violent reaction. And that's because the electrons are actually more loosely held in potassium. So this electron can be released much more easily, and a reaction occurs because electrons are rearranged in atoms because of electrons. So in the case of metals, metals give up electrons. So this potassium atom would give up an electron much more easily than the sodium atom, because sodium's electrons are held more tightly, is the idea. So the ionization energy is lower for potassium, so it's easier to remove the electron, so the reaction happens quicker, much more readily, and then much more violently. So something like cesium would be extremely reactive. Francium is usually not discussed in this reactivity trend because francium is extremely rare, one of the most rare elements, and it's also radioactive. So not much of francium has been played around with. Now there are two exceptions, really important exceptions to this trend, and these exceptions will allow us to see shells and subshells and orbitals. The first exception is when you remove the first p electron, and that would be here. So notice that from lithium to beryllium you increase in ionization energy, which is the trend that we see because they increase going this way. Ionization energy increases. But then you see boron having a smaller ionization energy than beryllium. Notice it's 801 as compared to 899. So that is the first trend, and that is, here it says removing the first p electron. This is the p electron, this is the whole p block. Remember, this is the s block. So when you remove this first electron, what happens is the configuration becomes S2, which is a filled subshell. And that's why the trend is there, why the break in the trend. And this actually proves to us our idea of subshells. And this is experimental evidence because these ionization energies are actually laboratory numbers, laboratory data, and that verifies our idea of subshells and shells. So the second exception happens right here. So if you keep climbing, then from boron on to carbon you increase, to nitrogen you increase, but then you see another decrease from nitrogen to oxygen. So the question is, why is this the case? And here it says removing the fourth p electron gives a half full sublevel. So here oxygen actually, remember we have 3 orbitals in the p subshell, and with oxygen what you'll do, here's nitrogen's configuration, with oxygen you have 1 more electron. Now when you put this electron in, what happens is there is repulsion that's developed between these 2 electrons. That's partly why this electron will be spun down, will actually attain an opposite spin, because to minimize that repulsion. So what happens is when you remove this electron, you become more stable, and that's why oxygen, it's easier to remove an electron from oxygen than it is from nitrogen, because oxygen has this repulsion kind of built in to the atom. And then once you attain a nitrogen configuration, you have a half-filled subshell. And this, kind of like the fully filled subshell of beryllium, a half-filled subshell gives you stability. Again, this verifies our idea of orbitals. And actually, Hund's rule, which means, this is from the last chapter, Hund's rule said that you put the up electrons in first until the orbitals are half filled, and then you put the down electrons in. And this actually is experimental verification of our theory. Now you'll see that the highest, and from then on, from oxygen it goes up to fluorine and neon. Neon has the highest ionization energy of the entire group. A good 4 times bigger than good old lithium that we started with. So the noble gases definitely have the highest of all ionization energies. These are the highest. And that is ionization energy. Know about the general trend, also know about the exceptions. Now, if we take a look at one element and just take a look at its ionization energies, you'll see that the first ionization energy is lower, the second is higher, the third is higher still. So every time we keep removing an electron, i.e. 3 would be removing the third electron, it progressively increases. The pull of the electron toward the nucleus actually increases. And that's what this says. The nucleus draws the remaining electrons closer to it. That's because there is repulsion between the nucleus and the electrons out here, and that repulsion, it's kind of like a tug of war. It's between the nucleus and the electron. If you remove one of the electrons, then the nucleus technically wins, the rest of the electrons get pulled in closer. Now, this actually measures a sodium atom losing an electron. What you'll notice is that the size of the atom, which is 186 pm is picometers, suddenly decreases to 97 picometers. So half as big, which is pretty significant, which shows you how strong that pull of the remaining electrons is. If we take a look at something like argon, here we list all 7 of its ionization energies. This again is kilojoules per mole. But you'll see that argon's first electron takes 1500, the second one takes about 2600. So between here and here, about 1,000, a little more than 1,000, about 1100 joules or kilojoules. Between here and here, it's more than 1,000. It's about almost 2,000, about 1,300. So not quite 2,000. A little more, not quite 2,000, 1,300. Between here and here is about 2,000, almost 2,000, so about 1,800 or so. So notice it progressively increases. That's because the nucleus keeps drawing the electrons closer and closer to itself. And so this is true for any element. You'll always see an increase in progressive ionization energies of the element. And here they designate it as EI. So instead of saying ionization energy, they say energy of ionization. So they kind of flip it. Energy of ionization. Alright, so here is a quick question. And is chlorine or chlorine minus 1 bigger, is the question. Now, since we realize that chlorine minus 1 has an extra electron, we should guess that that extra electron will cause the ion to be bigger. And you'd be exactly right. Chlorine as an atom has less electrons. If you gain an electron, is what this happened to this chlorine, the electrons are now winning, so technically they pull out, are able to expand a little bit, and the chlorine ion is actually bigger. So this would be the answer. If we do the same thing with a positive ion, like a metal, here's copper and copper 2+, two forms of copper. And copper 1+ has lost 1 electron. Anytime we put a plus, we mean a +1. Copper 2+ has lost 2 electrons, so the one that lost more electrons will be smaller. So this one should be quite a bit smaller than the copper 1. The original copper atom would be the biggest, obviously, but this one should be the bigger one. Alright, hopefully that makes sense. And we'll try one on your own. Go ahead and pause the video, try this, make sure you use the same logic. And then we'll finish up with this statement about ionic radius. And we'll say that cations are smaller than atoms. That's because they've lost electrons. And anions are bigger than atoms. That's because they've gained electrons. So here is another example. Here is fluorine. This is actually group 17. These are the halogens. 17, you'll notice that each time they gain an electron, and that's the characteristic reaction of halogens, they gain electrons to become negative, they get quite a bit bigger. In this case, 2 times bigger. Actually, most of the cases, 2 times bigger. Now, as you go down, so here from about 1, so about 2 times bigger, but here not quite 2 times bigger. So that trend isn't as pronounced as you go down the periodic table. But this is always true. Anions will become bigger. Alright, so this completes for us video 3.